Today, speaking our colloquium, we have Anna Romanov from the University of Sydney. Anna received her PhD from the University of Utah in Salt Lake City, and from there moved to the University of Sydney, where she's a NSF postdoctoral research fellow. Anna is going to be talking to us today about bridging two worlds, two of our examples of Beilinson-Bernstein localization. And what we're going to do is I've kept everyone's microphones muted. If you wish to ask a question during the talk, you can put something in the group chat or put the little hand up icon in the participants list if you want to ask a question, and we can pause and ask the question. Otherwise, at the end of the talk, I'll let people unmute themselves for question time if you want to ask a question at the end. So with that, I'll hand over to Anna to take it away. Thank you.
Great. Thank you, David. So I have to say that I was just absolutely delighted when I received the email from David a few months ago with an invitation to speak at Macquarie University, because even though I've never actually been there before, Macquarie University holds a special place in my heart. And this is because my maiden name is Macquarie. And when I was growing up as a kid in the Western United States, this was a really uncommon last name, and no one could ever pronounce my last name growing up. It was sort of this strange name that no one could say. And once when I was really young, maybe 7 or 8, a family friend went on a vacation to Australia, and they came back and they brought me a Macquarie University t-shirt. And I loved this t-shirt as a kid. And I wrote to my mom before this talk to see if she could find any pictures of me wearing this t-shirt, but unfortunately it seems that none of them exist. But in my mind, Macquarie University was always this mythical place on the other edge of the world that was so far away and full of people who could pronounce my name. And so I'm still just tickled by the fact that now I live in Sydney and I'm just down the road from this place that was kind of held a very special place in my childhood. So I'm very happy to be here at Macquarie, even if it is just virtually. Okay, so let's see if this thing gets going. So today what I want to do is I want to tell you about what I think is a very beautiful theorem. And right here, this is how the theorem originally appears in the paper. And we'll spend the rest of the talk talking about what it means. And so, of course, I don't expect you to know what it means right now. But this theorem was really influential in my field. And it's not a new theorem. It was proven almost 40 years ago in this tiny little 4-page paper. But it's a theorem whose influence is still omnipresent in representation theory. And it continues to affect the way that we approach problems. And what this theorem did is it really marked a turning point in the field. And I think that it's probably safe to say that representation theory as a field can be split into 2 different eras, the era before Beilinson-Bernstein localization and the era after. So it's a theorem that fundamentally changed the way we think about problems. So what I want to do today, my goal, is I want to try to explain to you why I find this theorem so beautiful. And I also want to try to explain to you how it shapes the mathematical world that I live in. And I realize that most of you in the audience are not representation theorists, except the small little Sydney crew that I brought with me. So I'll try to do this by using many, many examples. And so all of this will hopefully be done through the lens of examples to make it more concrete. But before we can get to this actual theorem, we need to back up quite a lot, just about 2 centuries. So, by the way, a little bit of history, and my reference for all of this is this book by Curtis called Pioneers of Representation Theory, which I say more precisely at the end of the talk. But on some level, people will often say, if you ask them, that representation theory is the study of symmetry. But symmetry's been present in mathematics for a whole lot longer than the words representation theory have. In the early 19th century, symmetry was around. I mean, it was around before this. The Greeks were thinking about it. And what did it actually mean at this point in time, around 1800? What did mathematicians mean when they were thinking about symmetry? Well, symmetry was a quality that some physical object could have. People would do things like describe the symmetries of a butterfly, or the Platonic solids, or a tiling of the plane. But then, around 1830, Galois came around and he viewed symmetry in a different light. So he realized that not only concrete physical objects could have symmetry, but polynomials could have symmetry too. And in his groundbreaking work, he coined the word group to describe these symmetries of polynomials. And this is often sort of taken to mark the beginning of group theory at this point in time. And as the century progressed, the study of symmetries via the language of groups continued to grow. So in the sort of mid-1800s, Felix Klein came along, and he, in his Erlangen program, he proposed that symmetries could completely describe geometries. So geometries were completely given by their symmetry groups. And so at this point in time, group theory entered into geometry. And then not so long later, Sophus Lie came along, and he described a new type of groups, which he called continuous transformation groups. And these had an additional structure. So they were still describing symmetries, but they changed in a continuous way. So they had the structure of a differentiable manifold as well. And at this point in time, groups entered into calculus. So by the late 19th century, where we were is that people realized the right way to study symmetries, the right mathematical language for this, was through the theory of groups. But what was less established was what was the right way to study groups. So in general in math, one strategy that appears all over the place is that if we have something we want to understand, like a group, one way to understand it is to not look at it directly, but instead to look at how it interacts with the other pieces of the mathematical universe that we understand better. So what's something that we understand particularly well? Well, linear algebra is something that we understand pretty well. So if we apply this mathematical strategy to groups in vector spaces, then we arrive exactly at the definition of representation theory. So what representation theory is it's the study of group actions on vector spaces. And here's where it first showed up, not so much longer in our timeline. So maybe this is the first representation theory that was ever published, this paper by Frobenius in 1896. And Frobenius was interested in group theory. He was interested in solving this problem of factoring the group determinant. And in doing so, he invented what's now called character theory and described it in this way. So at this point in time, this method for studying groups by looking at how they act on vector spaces is starting to emerge. But it's still not entirely clear that this is a good way to study groups, because remember, groups are what describe symmetries. These are the things we're interested in. And so is this actually a good way to study them? Well, here is someone who is skeptical. This is the introduction to a book that was written in 1897, just a year after Frobenius's paper with the first bit of representation theory came out. And this is a book by Burnside about group theory, and I'll just read out loud what he says. So he's talking about how to study groups and what the best way to do them. So he says that, oh, actually, I can't read it. Cayley's, oh, maybe I'll just read the last bit. The first bit of it's cut off for me. But the summary of this is that he's talking about what the best way to study groups are. And he says, he asks the question, why in a book which professes to leave all applications on one side, a considerable space is devoted to substitution groups, while in other particular modes of representation, such as groups of linear transformations, are not even referred to? My answer to this question is that, well, at the present state of knowledge, many results in the pure theory are arrived at most readily by dealing with properties of substitution groups. It would be difficult to find a result that could be most directly obtained by the consideration of groups of linear transformations. So groups of linear transformations, these are groups acting on vector spaces as matrices. So what he's saying here is that this isn't a good way to study groups. He can't think of an example of a way where this, of a time where this is useful. So this strategy was not uniformly absorbed, but eventually he changed his mind, as did many others. So here's the second edition of the same book. And in the second edition, he says exactly the opposite of what he said in this edition. So the second paragraph here, he says, in fact, it is now more true to say that for further advances in the abstract theory, one must look largely to the representation of a group as a group of linear substitutions. So what happened in this 11-year period, or slightly longer, between saying that this was not at all a useful way to study groups and saying that this was the most useful way to study groups? Well, actually, probably what happened is that he became aware of Frobenius's work, which he was unaware of when he wrote the first edition of his book. But why is this a useful strategy? So why is it more useful to study groups by seeing how they act on vector spaces? And one example of where this is particularly useful came up just slightly after this in our timeline, and this is in quantum mechanics. So right after this, 2 years after the second edition of the book, Niels Bohr came out with a quantum theory for the hydrogen atom. And soon after this, Heisenberg, Born, Jordan, and Schrödinger put out the first consistent theories of quantum mechanics. And this gives us a really nice example of why studying symmetries by studying representation theory can be helpful. So here's our first example. This is an example of the quantum system of the hydrogen atom. So if we look at the symmetry group of the hydrogen atom as a quantum system, this is the group of rotations in three-dimensional space, SO3. And the fact that this quantum system has symmetry can be expressed by saying that this group of symmetries acts on the Hilbert space of quantum states for this system. But what exactly is this? Well, SO3 is a group. A Hilbert space is the vector space. And so this is a group acting on a vector space. In particular, it's a representation. So the fact that symmetry is present in this hydrogen atom quantum system means that we naturally have a representation floating around. And then we can use what we know about representations to tell us information about the quantum system. So using things that we know about representation theory of SO3, we can decompose this representation and obtain information about the base states of our quantum system. So in situations like this, we see that studying symmetry through looking at group actions on vector spaces is a nice way to go. So if we sum this up a bit, the transition throughout the 19th and early 20th century was the following. We started out by wondering about symmetry and then moved on to studying this in the language of group theory, and moved on from this to studying this through the language of representation theory. And this is the setting of today's talk, representation theory. So one class of representations that are one class of groups that are particularly interesting are these ones that I mentioned earlier. They were introduced by Sophus Lie, these things called Lie groups. And these are groups that have an additional structure. They're a group, but they're also a manifold. And so what are some examples of these? Well, we've seen one example so far. This is the example of SO3, rotations in three-dimensional space. Another example is just the circle. So the circle here has the structure of a group. We can take the group law to be composition of rotations, and it also has the structure of a manifold. And one more example, an example that will play a prominent role in the talk today, is SL2C. So this is an example of 2x2 determinant 1 matrices with entries in C. And this thing is a group because we can multiply together to 2x2 determinant 1 matrices and we get another one. And it turns out that it also has the structure of a manifold, and so it's what's called a Lie group. But there's nothing special really about the size of the matrices here or the field C. We could look at n by n invertible matrices in R, and this would also have the property that we could multiply together two matrices and get another one like this. So this thing forms a group. So this is the class of groups that we'll be looking at today, Lie groups. And it turns out that much of the information about a Lie group can actually be captured in a simpler object called the Lie algebra. So since a Lie group is a group and a manifold, it has an identity element, and it also has a tangent space at each point. So in particular, we could take the tangent space at the identity element, and this a priori is just some vector space, but it turns out that this vector space, because our underlying manifold had the structure of a group, this vector space has some additional structure, which makes it into something called a Lie algebra. So here are some examples of these things. If we took the circle group from earlier, S1, and we looked at its tangent space at the identity, well, this just looks like a copy of the real line. So the Lie algebra of S1 looks like R, but it has this extra structure of a Lie algebra. And then our favorite example, if we take 2x2 determinant 1 matrices, and we do this process of taking the tangent space at the identity, what we get, we differentiate this determinant 1 condition, and we get 2x2 trace 0 matrices with complex entries. And this is called the Lie algebra, little SL2C. And it turns out that this procedure of going from a group to going from an algebra, we can do this with representations too. So if we have some representation of a Lie group, we can differentiate this and we can get a representation of a Lie algebra. So we can get a vector space with an action of a Lie algebra. So if we're interested, remember we were interested in studying groups, so we studied them via representations. And now we're interested in studying representations of these special types of groups, Lie groups, and we can study these through representations of Lie algebras, which are slightly simpler objects. So our new plan can be to study vector spaces with actions of Lie algebras. And this lands us into the world of representation theory of Lie algebras. So now we're in this world where we're interested in vector spaces with Lie algebra actions. And maybe a natural question when you're encountering a new world is a classification question. This is the thing that we try to do a lot in math. So you might ask yourselves if we can describe all of these. So is it possible to describe all possible vector spaces that have an action of a Lie algebra? And here, for the rest of the talk, I'll mention that I'm only considering nice Lie algebras. And it doesn't matter what these words mean, but for me, nice is complex, semi-simple. And you'll see, you can always just keep in your head SL2C, 2x2 traceless matrices as an example of one of these. And the philosophy behind this question is that we want to understand the Lie algebra because we want to understand the Lie group. And we can understand the Lie algebra by understanding all possible vector spaces which admit an action of this Lie algebra. Okay, so if this is our new plan, how are we going to go about it? Well, a starting place is to look at the building blocks. And in representation theory, the building blocks are what are called irreducible representations. And so what this means, we say that a representation is irreducible if it doesn't have any subspaces which are stable under the action. So remember, a representation is just a vector space with an action of G that shuffles around the vectors in some way. And so if we can't find any subspaces where the vectors are just shuffled around within the subspace, then our representation is irreducible. In some sense, we're saying that G completely mixes up the vector space. And if, furthermore, the representation that we care about is finite dimensional, so if we have a finite dimensional vector space with an action of a Lie algebra, then it actually decomposes into a direct sum of all of its irreducible representations. And so what this means is that in the case of finite dimensional representations, the building blocks really are irreducible representations. You can describe every finite dimensional representation of one of these nice Lie algebras by decomposing it into a direct sum of irreducible pieces. Okay, so if our problem is understanding representations of Lie algebras, we sort of have two bits to this now. Now we have to understand how we can build them, and the answer is that we just build them by taking direct sums of irreducible ones. And the second question is, what are all the possible irreducible ones? And it turns out that the second question has a very nice answer in this setting. Irreducible finite representation can be classified in a way by something called highest weight. So I'll describe this just through an example. So here's our favorite Lie algebra, SL2C. I remember these are 2x2 traceless matrices. And so what I've done here is I've chosen a basis for this Lie algebra. Every traceless 2x2 matrix can be written as a sum of this matrix F, this matrix E, or H, and this matrix E, with some coefficients. And this color coding is going to show up throughout the talk, so I'll try to always keep them in the same colors. And this classification by highest weight for SL2C is saying that every irreducible finite dimensional representation is uniquely determined by some non-negative integer. So for example, if we choose the non-negative integer 2, we can build a representation that looks like this funny picture over here. And so let me take some time to explain what I mean by this picture, because these dots and lines pictures will have an appearance throughout this talk. So this is supposed to be a picture of a representation. But what is a representation? It's a vector space with an action. So how is this a picture of a vector space? Well, each of the dots that I have in this picture is a basis vector. So I've chosen a basis for my vector space, and it's a three-dimensional basis, or it's a three-dimensional vector space because it has three basis vectors. But it's not just a vector space. It's a vector space that has an action of this Lie algebra, which is also a vector space. So if I want to describe the action, I just need to describe how these three basis vectors, F, H, and E, act on my three-dimensional vector space. And the actions are given by the arrows. So, oh, maybe this is the right time to use this pointer. Spotlight. So this arrow here, that's not what I want. Undo. So this arrow here is saying that if I take this basis vector, the vector space, and I act by the matrix H, I come back with 2 times this basis vector. which is just saying that this basis vector we've chosen is a 2 eigenvector for H. And same with this one. This is a 0 eigenvector, and this one is a -2 eigenvector. And then these other arrows are saying that if we act on this basis vector by the matrix F, we end up with 2 times this basis vector. If we act on this basis vector over here times the matrix, or act by the matrix E, we end up with a copy of this basis vector. So we can see from this picture that this completely describes the action of SL2. It tells us we can write all vectors in the vector space as linear combinations of the basis, and this tells us exactly how these 3 matrices shuffle around the basis vectors, so it completely describes the representation. And we can also tell by looking at this picture that this representation is irreducible, because we can get from every one of these basis vectors to every other basis vector just by moving around in our arrows in some way. And so this classification of irreducible finite dimensional representations by highest weight is saying that all of these representations have this nice form. They're determined by non-negative integers, and they have this nice structure that we can draw. Let's get rid of this. Okay, so that was all very nice. Remember, our strategy was we were trying to classify all representations, and we started with finite dimensional ones, and the story was pretty simple. It was they all break down into building blocks, and all the building blocks are uniquely determined by their highest weight. But it turns out that if we keep going and move up to infinite dimensional representations, the story suddenly becomes much more complicated. One problem is that our semi-simplicity we had in the finite dimensional case goes out the window. So every one of our finite dimensional representations as a direct sum of its irreducible pieces, and this is no longer true if our representations are infinite dimensional. Another problem is just that infinite dimensional vector spaces are kind of wild. A lot of our tools in linear algebra work great on finite dimensional vector spaces, but as soon as we move up to infinite dimensions, things are a little bit more complicated. So you might be wondering at this point in time, if we even really need to care about infinite dimensional representations. I mean, the finite dimensional ones were great. Why do we need to care about these infinite dimensional ones as well if really all we want is to understand the Lie algebra? And the answer to this is yes, we do. And this is because many of the representations that we encounter in nature in some way are often described in terms of functions on spaces. So functions on algebraic varieties or manifolds. And function spaces are often infinite dimensional. So if you remember, we've actually already seen an example of this. In our hydrogen atom example, the Hilbert space of quantum states was given by L2 functions on the sphere. And this is an infinite dimensional space. So unfortunately, we do need to consider infinite dimensional representations, even though they are messier than these finite dimensional ones. But in the 70s, people came up with a strategy for how to tackle these things. So the strategy was the following, that maybe if we impose some restrictions on our representations, so we don't try to classify all possible representations, but we just look at representations that have some nice restrictions, then we can find categories within the chaos and study the structure of these orderly categories of representations. And then we can try to relax the restrictions and see what happens, see what bits of structure carry over as the restrictions are relaxed. Now, the quintessential example of this is this category called category O. So this is the category of representations, and it contains all the finite dimensional ones that we studied. So it has the nice finite dimensional representations in it, but it also has plenty of infinite dimensional representations as well. And it also has the property that objects in this category are finite length. So remember that one of the main problems when we moved from finite dimensional vector spaces to infinite dimensional vector spaces is we lost semi-simplicity. And without semi-simplicity, there's not necessarily a nice notion of building blocks. What does it mean for a representation to be built from other representations if we can't decompose it into a direct sum of them? And so this notion of finite length lets us have some idea of building blocks, even if our representations aren't semi-simple. And so what it means for a representation to be finite length is that the vector space has some filtration by subspaces, and each of these subspaces is a sub-representation. So they're stable under the action of the Lie algebra. And if we take the quotient of one subspace by the one below it, we end up with something irreducible. So we can't necessarily write V as a direct sum of its irreducible pieces, but it still has these irreducible subquotients in its filtration that are well defined. So it still makes sense to talk about a representation being built by irreducible representations. Okay, so we have some representations, and it turns out that they have a nice classification that generalizes the classification of finite dimensional ones that we saw earlier. So I'll give this classification briefly, and I'll keep a running example of SL2 to keep us grounded. So how does this classification go? Well, our first step is that we pick a certain subalgebra of our Lie algebra. It doesn't really matter what these words mean, but it's something called a Cartan subalgebra. And in the SL2 example, this is just all the diagonal matrices. So it's the C-span of this matrix H, which I haven't told you what the matrix is, but this is the same one as we had earlier. It's the matrix 1, 0, 0, negative 1. And then we look at things in the dual of H. So this is just the set of linear functionals from H to C. And for each of these linear functionals, we build a representation. And so here's an example of what one of these looks like. If we're looking over here in SL2, and we choose the representation that sends H, which is our generator of this subalgebra, to 2. That completely describes some linear functional in H star because H is just generated by one element. Then the corresponding Verma module we can build has a picture that looks like this. So again, this is supposed to be a picture representation. So this is a picture of a vector space with an action of SL2C. But in this case, again, the dots are basis vectors for our vector space, but there are infinitely many of them. This thing continues on to the left forever. And so now this is an infinite dimensional representation, but the action is still very nice. So still we have this property that the actions of these 3 matrices are just described by taking one basis vector to a multiple of another basis vector. And our basis vectors can be chosen so that they're all eigenvectors for this matrix H. Oops. And so then the next step in the classification, these dimensional modules that we've built has a unique irreducible quotient. So if we look at our example over here, our Verma module is generated by, I should go back to the pointer, that was useful, is generated by this vector here. Because if we take this vector and start acting by blue arrows, we eventually get everything along the line. But it has a submodule because the red arrows that are going in the opposite direction are weighted by these numbers, and at some point we get 0. So if we start with this vector right here and act by blue arrows, we can get all the way down the line as far as we want. And if we start acting by red arrows, we can come back up. But once we get here, the red arrows kill the vector. So there's no way to get these other 3 basis vectors once we've gotten to this point in time. So what this picture is saying, the fact that we have a 0 here in our line, means that this Verma module has a submodule. And if we take the quotient of the entire module by this submodule, we end up with something that looks just like the finite dimensional module we saw earlier. So it's a 3-dimensional representation, and it's exactly the one that we saw before. It has the same action. And so it turns out that for any choice of linear functional, we could have sent H to anything in C, we could have built a similar module, and they all have they have a unique irreducible quotient. Oh, that's the last bit here. So every irreducible representation in our nice category shows up in this way. So for SL2, this is saying that all irreducible representations, they're in bijection with complex numbers. So what's the takeaway from this? Well, the takeaway is that this category of representations, that I haven't told you exactly how it's defined, but it's a category that's very nice. It contains infinite dimensional representations, but they're sort of orderly in some way. And the classification of irreducibles shows us that this category decomposes into pieces, into blocks. And each of these blocks, if we look at its corresponding Grothendieck group, it has 2 natural finite bases, one coming from these irreducible modules, and one coming from the Verma modules that we use to build them. Because part of the classification that we saw in the previous slide was that the way that we come up with all the irreducible objects in our category is we first build some other object, and then the Verma module, and find the irreducible objects within it. And so this structure means that the category has these 2 different classes of distinguished objects. And so a natural question is how these 2 different classes are related. So every object in the category can be written in terms of Verma modules, and it can also be written in terms of irreducible modules. And so this gives us, this gives us two different bases, and we can ask about the change of basis matrix. So how are Riemann modules and irreducible modules related? And this question turned out to be surprisingly difficult. Well, maybe not surprisingly, but here's the conjecture about how it goes. So to a Lie algebra, like SL2C, there's an associated finite group, which is called a Weyl group. And SL2C gets associated the group Z mod 2Z. And in 1979, Kasdang and Lustig made a conjecture about how to relate the Riemann modules and the irreducible modules using this finite group W. And their conjecture was that the change of basis matrix that describes how Riemann modules and irreducible modules are related is determined by a collection of recursively defined polynomials in one variable that depend only on the Weyl group. So this is kind of crazy. This is saying that most of the structure of this category of representations is determined by a finite group. So these are representations of Lie algebras, which are somewhat complicated objects. They're supposed to be describing Lie groups, which are groups and manifolds. They have a lot going on. But this is saying that these representations are determined, or their structure is determined by something much smaller and finite. And now our story has finally arrived at the place that I told you it would arrive at the beginning, which is the beautiful theorem that I showed you a picture of earlier. So remember that this conjecture was made in 1979, and in 1981, the conjecture was proven simultaneously by two different parties. Beilinson-Bernstein was one, and Berlinski-Kashiwar was another. And they proved the conjecture using similar methods, and both of their methods relied heavily on geometry. So to prove this relationship that was conjectured by Kasdang and Lustig, Beilinson and Bernstein built a bridge. And what their bridge did is it was a way of going back and forth between representations of a Lie algebra and something completely different, something called D modules on a flag variety. So on one side of this bridge were objects in representation theory, representations of Lie algebras, and on the other side of the bridge were objects in algebraic geometry, D modules. And so far in this talk, we've discussed the left-hand side quite a bit. We've talked about representations, but what are these things on the other side? So now the talk's going to take a bit of a turn, and we'll talk a little bit about what were the objects on the other side of the bridge. So if we start with a Lie algebra, there's an associated algebraic variety called the flag variety. So for SL2, the variety we get is just the sphere, or CP1. And what D modules are is they're sheets of modules variety over rings of differential operators. So what does this mean? Well, locally, it just means that they look like a vector space with an action of a special ring, but it's a ring of differential operators. So it's a ring that is spanned by a bunch of things that look like differentiation with respect to some complex variable and multiplication by that complex variable. But globally, they're glued together in some sort of complicated way that depends on this parameter lambda. So the upshot of this is that what Beilinson and Bernstein did is they let us translate questions about representation theory of Lie algebras into questions about algebraic geometry. So why is this actually helpful? Why is this a good strategy? Well, it turns out that algebraic geometry has some really powerful tools which representation theory lacks. And one of the main tools is this theorem called the decomposition theorem. And so what Beilinson and Bernstein did is they used their bridge to prove this conjecture of Kasdang and Lustig about how Riemann modules and irreducible modules are related to each other. Their bridge told us how to go back and forth between representations of a Lie algebra and D modules. And category O was a special class of representations of a Lie algebra. So what they realized is that the corresponding D modules over on the algebraic geometry side of the bridge were these D modules which were n equivariant for some Lie group n that was showing up in the picture. So what happened is that this brought about a new era of representation theory. It changed the way that we think about problems in the field, because in order to solve this conjecture, they actually brought about something much bigger. So their statement, notice here, they were trying to prove something about category O, but their statement, it applies to basically all representations of G with a small stipulation that we have to say how the center of the universal enveloping algebra acts. But this is a much bigger statement than just a statement about category O. And so this theorem changed the way we look at problems, because it showed us for a while, at least for 30 plus years, until somewhat recently in 2014 with work of Elias Williamson, that this question that Kosdong and Lustig posed, which was a fundamental question in representation theory, only had an answer that used geometry. So in some sense, it sort of tied the fields together in an inseparable way. And it also, the other thing it did is it made it clear to us that this attempt that I proposed to you at the beginning, this idea that we should study Lie algebras by studying all possible representations, was actually kind of an unreasonable question to be asking in the first place. And it wasn't what we should be aiming for. So to see this, we can look quickly at the example of SL2 again. So what Valence and Bernstein's theorem says is that SL2 representations should correspond to D modules on the sphere. Well, here's one way to build D modules on the sphere. I think this is exactly quite right. If we take the sphere and take away a bunch of points on it, then the fundamental group of what we get is a free group on, actually four generators. And so for each representation of this fundamental group, we can build ourselves a D module on the sphere, which we can then use to, or we can build ourselves a D module on the punctured sphere, which we can then use to build a D module on the entire sphere. And so what this is saying is that for every representation of a free group of any size, we can build ourselves a D module. But then if we walk this back across the bridge, we're supposed to have a corresponding representation of our Lie algebra. So this is telling us that the representation theory of all possible free groups is contained in the representation theory of Lie algebras. But free groups have no structure, they're wild. And so classifying this problem of representation theory of Lie algebras is just absolutely huge. And it's not really a thing that's going to have any sort of reasonable answer, even though we can find categories like category O within this huge question that have some nice structure. So the upshot of all this is that we should change the way we're thinking about questions. So what happened after Beilenson-Bernstein localization is that we abandoned classification questions and instead started thinking about representations that had significance and relied heavily on geometry for intuition as to how things should go. Okay, so I promised you, well, maybe I promised this in the abstract of my talk, that I would give this through many examples. And maybe so far I haven't delivered too many examples. So the last part of this talk is on trying to get some sense of what these D modules look like in our example of SL2. So the plan for the rest of the talk is that I want to draw you some D modules on a sphere and walk them across this bridge of Beilenson-Bernstein localization to see what we get on the other side, see what representations they correspond to. So here's our setup. The space that we're looking at now we're sort of living in the land of algebraic geometry, is P1, which I'll think about as a sphere. You can think about it as lines in C2 if you'd rather. But if we think about it as a sphere, it's clear here that it has two charts, which each look like a copy of C. I can take this sphere and remove the North Pole, or I can take this sphere and remove the South Pole. And each of these things looks like a copy of C. And so what is this sheaf D that keeps showing up? Well, this is a sheaf of differential operators on the sphere, which just means that on each of these two charts, it's a ring. So on the chart C0, where we remove infinity, this is a ring of polynomial differential operators in one variable, which just means it's a ring generated by differentiation with respect to Z and multiplication by Z. And on the other chart, it's a ring in some other variable, but the way that these two variables are related is that they're inverse to one another. So this object here, this sheaf of differential operators, is really just two rings with some gluing data. And what we want to think about are modules over this sheaf. So what is a dx module? Well, like the sheaf itself, it is a sheaf, but it's completely determined by just two vector spaces. a vector space on our chart, which doesn't have 0, and a vector space on our chart, which doesn't have infinity. And these two vector spaces come with an action of the corresponding ring of differential operators. And these actions have to be compatible in the same way as they were glued together originally. So if we want to describe a D-module, at least in this case of a D-module on a sphere, we can describe it as a pair of vector spaces with an action of this pair of rings. Okay, so let's try to see. Here's one example of these. We could look at the sheaf of regular functions on our sphere. And all this means is that if we look at the sheaf on any open set, it just looks like polynomials on that open set. And so in particular, if we look at this sheaf on the first chart that we have, which is the entire sphere minus infinity, this looks like polynomials in the variable z. Now, this is our first vector space, C of z. Again, I'm going to draw it using these dots and lines pictures as I did before, and it has a basis just spanned by monomials. And the action of the differential operators that make this into a module are given in these colored things here. So this here is just the regular action that you would expect if we differentiate a polynomial, or if we multiply it by z. So if we differentiate z squared, we end up with twice z, so we end up at this basis vector. So all this picture here is saying is it's a funny way of looking at everything that we already know about differentiating polynomials in one variable. So this is what our sheaf looks like on one of our charts, and on the other chart, it looks the same. We just now have the variable w instead of the variable c. So this here is meant to be a picture of the D-module. It tells you what it looks like on each of the open sets. And Beilinson-Bernstein's bridge said that D-modules are supposed to correspond to representations. So what representation is this D-module? Well, what I hadn't told you yet was how to go back and forth between D-modules and representations. And it turns out the way to do so is with this functor called global sections. And so if we apply that in this case, we see that the global sections of this sheaf are just polynomials in z, which are also polynomials in w. But remember that the relationship between z and w is that w is the inverse of z. And so the only polynomial that can be a polynomial in z and in w is just some number, scalar multiple of the identity. And so the global sections of this D-module give us the trivial representation of SL2. Okay, so maybe that wasn't the most interesting example, but we can do another that's maybe slightly more interesting now that we've warmed up a bit. So here's another picture of a D-module. We can build a D-module in the following way. So previously we looked at the sheaf of regular functions on the entire algebraic variety, but instead we could look at the sheaf of regular functions on one of our charts, so this C infinity, where we take off the north pole of the sphere. And then the D-modules come with this whole host of functors that we can use to push them around. And so if we take the sheaf just on the chart C infinity and push it forward to the entire variety P1, this procedure is going to build us another D-module. And it turns out that the D-module we get looks something like this. Well, on the chart that it came from, which is the chart C infinity, it looks the same as the other D-module did, because this sheaf of regular functions on C infinity is just going to be polynomials in one variable, the variable corresponding to that chart. But if we restrict it to the other chart, the one that includes 0, we get something that looks a little bit more complicated. And this is all bunched up in what it means to be this D-module push forward functor. So this is another picture of a D-module. This is what it looks like on each of the charts. We have an action of differential operators, which is given by these arrows. And so we can ask ourselves the same question we asked before, which is what representation does this correspond to if we walk it back across the bridge of Beilinson-Bernstein? And it turns out that this D-module corresponds exactly to one of the Verma modules we saw earlier in category O. And the way that we can see this needs a lot more work than I can do in a few minutes in a talk, but the idea is that we can assign differential operators to each of our basis elements of our Lie algebra in a certain way. And if we figure out what differential operators the Lie algebra basis element acts by, we can write down the structure of a G module on the global sections of this D module that I drew for you on the previous page. And we can sort of see what's going on if I move back a little bit. Oh, here's where I should use the pointer again. If we look, what's actually happening is the global sections are picking out for us exactly this part of the D module that we saw before with these arrows. This is the part that shows up in the global sections that looks exactly like a VRMA module. Okay, so maybe the upshot of this, which I didn't write down, is that this representation, or this D module that we built, is a very natural D module. We've just started with something that looks like functions on a piece of the sphere and pushed it forward to the entire sphere. And what we ended up with was a VRMA module. Oh, a VRMA module. So here's one last example, and after this example, I'll end. But there's another way that we can do a similar procedure with D modules that's very natural. And this is if we have the same inclusion that we did before, where we include the sphere, where we subtract a point into the entire sphere. But instead of looking at regular functions on this, we look at these exponential functions. So we look at the span under this ring that's spanned by d, dw, and w of an exponential function in one variable. And this thing has a structure of a D module, and we can push it forward to the entire variety in the same way we did before with functions. And we get a D module that looks slightly stranger. So what do these pictures mean now? Suddenly, this is the first time that my lines have gone to two basis vectors at once. And all this is saying is that now we have linear combinations. So if we look at this basis vector w cubed e to the w, and we act by ddw, this is exactly saying everything you know about differentiating this function with respect to one variable. So if we differentiate this, we get the same thing back again, plus twice w squared ew. And so this arrow is just telling us about a linear combination when we act by this operator here. So these D modules are a little bit strange, but they're still very natural. We're just looking at exponential functions on the sphere, and they result in this class of D modules. But again, Valence and Bernstein bridge there tells us that these should have corresponding representations of Lie algebras. So what representations are they? Well, it turns out if we write things down, we end up with a representation whose picture looks something like this. So suddenly this thing is a little bit crazy, but this has the structure of what's called a Whittaker module. And so the upshot here is that looking at these D modules that are pretty natural, exponential functions, they lead to an interesting class of Lie algebra representations, which are not in category O. So this representation here doesn't show up in that category that we saw earlier. And the reason I wanted to get to these is because these are actually the land where my research lies. So we can build a whole category of representations in this way by looking at these exponential D modules. And the words to describe them are twisted and equivariant D modules. And then we can see the representations that correspond to these. And these representations, they show up naturally in other settings as well. For example, in understanding representations of real reductive Lie groups. But it turns out that they're sort of tricky to study algebraically. And this has to do with the fact that they are very roughly more infinite dimensional than VRMA modules, or those representations in category O. So they're a little bit more unruly. But geometrically, they have a really nice description in terms of these exponential D modules. So the geometric framework of Valence and Bernstein is a very natural place to study them. And it allows us to answer questions about them in questions of the same flavor as the Coston-Lustig conjecture in this other setting. And this was work that I did in my PhD thesis called a Coston-Lustig algorithm for Whittaker modules, which answers a question very similar to the Coston-Lustig conjecture in this different setting of Whittaker modules. And I think I'm just exactly out of time, so I will end right here. Thank you.
Thank you very much. Okay, so thank you, Anna. I'm now going to let people choose to unmute themselves. Just give me a second here. Where am I? To ask any questions. Okay, so if anyone has a question, you'll be able to unmute yourself and fire away. do we have any questions? I can see someone's unmuted themselves. I can't hear anything. Is someone trying to ask a question?
Oh, was that me? No, I was just going to say thank you. Oh.
Okay, anyone, any last chance? Okay, so obviously the slides are available, and for Macquarie people, we'll have a link to the recording, which we can probably pass on to you, Anna, if you'd like it. So people can't unmute themselves. Sorry about that. That's my fault. I'm not sure. You should be able to unmute yourselves. If I can unmute people if they would like to ask a question. If you want to type something in the chat, I can unmute people one by one. Sorry about that.
Ah, that did it.
Okay. If you go over to the bottom left-hand corner, you should be able to click on the unmute button for everyone else.
Yeah, that wasn't working before, David.
Oh, sorry about that. Would you like to ask a question?
Yeah, thanks. Thanks very much, Anna. That was a great talk. Very interesting. Do you have is there some sort of version of Category O then that you like to think of your representations as sitting inside?
Yeah, there actually is a beautiful category that contains Category O. So it's described really nicely by Milicic and Zorgel. So you can actually do the procedure that I described at the beginning, where you take the restrictions and just relax them slightly. So I never actually told you how Category O is defined, but if you take one of the defining restrictions and just relax it a tiny bit, you end up with this bigger category that includes these Whittaker modules, and it still includes Category O. And then the character theory in that category specializes to the cause-stylistic conjectures for Category O, but also includes a more general framework. But it's hard to go much further. I think if you tried to relax the restrictions more, you'd sort of end up in chaos. So this Whittaker category is a nice in-between where it's slightly more chaotic than Category O, but you can't push it too much farther. It's already getting sort of weird.
Thanks.
I had a question as well. So at the end you talked about these, so this category you just talked about involves twisted versions of the things you said corresponded to the things that were in Category O.
Yes.
So, I mean, twisted turns up in lots of contexts and can mean lots of things, but in particular you could, so I'm wondering if it's something to do with, so you can look at differential rings, but then you can also look at kind of either, you might say, skew differential rings, where there's some kind of extra factor involved there. Is there some relation with this use of twisting here or not?
Perhaps. I'm not sure what skew differential rings are, but basically, go ahead.
It's where your product rule has a sort of a Q factor or something like that appearing in one of the variables.
Oh.
Maybe it's completely unrelated, but I mean, it's
it might be able to be formulated in that way. What the twisting means, one way you can describe them is, I wrote them down in terms of exponential functions, but you could have also written them down in terms of just polynomials, where you ask that the differentiation is twisted by some character. So you ask that like d dz acts on z to the n by regular differentiation, n times z to the n minus 1, plus some number times z to the n again. So you're asking that differentiation with respect to z actually acts like d dz minus c or something for some c.
right.
And so that sounds sort of similar.
Yeah, right. Because maybe it's not a differential ring, but it might be one of these skew differential rings, perhaps.
Yeah, but I think that but that same condition is just saying that differentiation acts on polynomials as if it were acting on exponential functions. So that's why I phrased it that way. It's often a little bit more natural.
Thank you.
Okay, so people should definitely be able to unmute themselves now if anyone else has another question. Looks like we're not. So let's finish there. Thanks very much, Anna, again, for that very interesting talk. And thanks everyone for coming.
Yeah, thanks for having me.
Very good.